Okay, so question 18. In order to save some time for you guys, instead of me talking through every step and writing everything out at the same time, I've written out the full work solution with all the workings so that you can pause the video wherever you need to and I don't have to talk as much. That would be the goal. So first thing I did was I pulled apart the question. Now, all of this is information that is given to you in the question. Then the next thing is that I know that because we're given a function for acceleration, I can do some fun math to figure out the velocity of our function. And then the velocity is the stuff that we're actually caring about, because once I have the velocity, I can substitute in 0.5 to find that. And I can use this when velocity is 0 and x is 5 to work out the constant value. So here's what we did. First, I set out our function as the mass, which is 5, multiplied by the acceleration, is equal to the force. Now, I factorised the bottom of the expression to get 3 different brackets, and then I moved the 5 across so that I've got an expression for A on its own. So once I cancel out the 5s, because I can factorise a 5 out from here too, they will cancel and I'll be left with this expression. Now, it's hard to integrate something like this, and we don't really have a formula for it. So if we use partial fraction decomposition, we'll end up with 3 separate terms, and then that's something that we can integrate. So you'll see in a little bit that that's the route that we're going to follow. Now, the next thing that I need to do, though, before I can start splitting up my fractions, is I need to work out which expression for velocity is the one that we want. So you can see here that this expression has all x's in it, which means that I want the denominator of this to have an x. And I want to choose the expression that has the velocity. The other one that could possibly look appealing to you at this point is the one that looks like dv over dx is, and then v there. If I take this to the other side to make this side the integral, then I'm left with the v here and the v there. It just doesn't work. So that's why we end up with this one. So now I'm at this point, I can use partial fraction decomposition. So this is what I eventually want my fractions to look like, which means that if I made the numerators all the same, I'd have to do this one times that one, this one times that one to figure it out. So that will make all of the bases to be this bracket times that bracket times that bracket, which is why I don't bother expressing all of them anymore. Now, we're going to use the null factor rule for each bracket to find out what needs to be substituted in. So if I make this one equal to 0, then it's going to be 0. If I make this one equal to 0, then x will be equal to 3. If I make this one equal to 0, then x will be equal to 4. So that's how I ended up with that step. Now, I substituted it into the expressions. I separated them out, substituted it in to find out what A, B, and C are equal to. From that point forward, I rewrote my fractions in our pretty form, and then I've integrated them. And it's hard to continue when you're throwing cones at me. Stop it. So now, ow, that one got me. Okay, so now the next thing that we're going to be doing is we're going to integrate this side and we're just going to leave the v squared alone. So when I integrate it, this is what I end up with on that side, plus the c. Now I can substitute in that when b is equal to 0, x is equal to 5, and then I do that down here to work out the value of c. All right, so now I've got v squared is equal to everything that was originally there plus our c value, and now I can let v equal 0.5. From here, I can g-solve to find out that my value of x is at 5.08 meters, which is our final answer for this. You could have also G-solved at this step here if you wanted to find C, but it wouldn't have given you an exact value. From what I can tell, I don't think that you get marked down for not having an exact value in that spot. All right, happy days.